Welcome to the session on Fourier integral representation of a function. In the applied mathematics, there are many situations to represent a given function in terms of trigonometric sine and cosines. The Fourier series, if the function is a periodic function, then we can use the Fourier series representation in order to represent the given function. If the given function is non-periodic, we cannot use the Fourier series representation. In this case, there is an alternative method to represent the given function in terms of sine and cosines, which is the Fourier integral representation. First of all, we have to state an important theorem, namely Fourier integral theorem. Before introducing the Fourier integral theorem, you have to know the Dirichlet conditions. A function satisfies the Dirichlet conditions in an interval I if the following conditions are held. First one is the given function is bounded. The second one is the given function has at most finite number of maxima or minima. The function has at most finite number of maxima and minima. This is the second condition, and a finite number of discontinuities. If these three conditions are satisfied by a function in an interval I, then we can say that the given function satisfies the Dirichlet conditions. Now, we have to state the Fourier integral theorem. The statement is if f of t satisfies the Dirichlet conditions on every finite interval, and if integral from minus infinity to infinity f of t, absolute value of f of t, that is modulus of f of t dt, is less than infinity, then f of t can be represented as an integral which is equal to integral from minus infinity to infinity 1 by 2 pi integral minus infinity to infinity f of t into e raised to minus I omega t dt into e raised to I omega t d omega. That is, the given function can be represented as an integral where f of t is continuous. At all points, the given function is continuous. We can represent like this. F of t should be continuous. And if there is a point of discontinuity, the value of this integral will become the average of right hand limit and left hand limit of the corresponding point of discontinuity. that is 1 by 2 into f of t plus f of t minus, where f of t is discontinuous. At all points of continuity, we can represent the function f of t as this integral. If there is some discontinuities, then we can write the right hand side as the average of left hand limit and right hand limit of the corresponding point of discontinuity, which is the Fourier integral theorem. Now, consider this integral representation f of t equal to integral from minus infinity to infinity 1 by 2 pi integral from minus infinity to infinity f of t into e raised to minus I omega t dt into e raised to I omega t d omega. Here there are two integrals. This integral here the inner integral is with respect to t, integration is with respect to t, and the outer is with respect to omega. We replace t by tau in this inner integral. We can write this as in the inner integral. Then we can write this as f of t is equal to integral from minus infinity to infinity 1 by 2 pi integral from minus infinity to infinity f of tau into e raised to minus I omega into tau d tau into e raised to I omega t d omega. We just replaced t by tau in this inner integral only. We can write like this. Now, here the limits of both integrals are from minus infinity to plus infinity. Therefore, we can consider this as a double integral. Therefore, we can write this as f of t is equal to integral from minus infinity to infinity, double integral minus infinity to infinity 1 by 2 pi into f of tau e raised to minus I omega into tau d tau into e raised to I omega t d omega. Here we can write like this. This into e raised to I omega t d tau d omega. That is, we just expressed this as a double integral. Now, consider this term e raised to minus I omega tau into e raised to I omega t, which is e raised to I omega into t minus tau. That is equal to, we can write cos omega t minus 2 plus I into sin omega t minus tau, because e raised to I theta is cos theta plus I sin theta. Here instead of theta it is omega into t minus tau. Therefore, we can write this as cos omega into t minus tau plus I into sin omega into t minus tau. Therefore, this is equal to, we can write this as integral from minus infinity to infinity, sorry, double integral from minus infinity to infinity 1 by 2 pi f of tau into here cos omega t minus tau plus I into sin omega t minus tau. D tau d omega, we can write d omega into d tau. By changing the order of integration, we can write d tau into d omega as d omega into d tau. Here both the limits are same. This is equal to double integral minus infinity to infinity 1 by 2 pi into f of tau into cos omega, we have to split into 2, cos omega t minus tau d omega d tau plus I into double integral from minus infinity to infinity f tau 1 by 2 pi into f tau into sin omega t minus tau d omega d tau. Now we just split into two integrals. This is equal to integral from minus infinity to infinity into integral from minus infinity to infinity 1 by 2 pi f tau cos t minus tau d omega d tau plus I into integral from minus infinity to infinity into integral from minus infinity to infinity 1 by 2 pi f tau into sin omega t minus tau d omega into d tau. Here cos t minus tau, here there is a correction, omega into t minus tau, therefore here also omega. Now here the integration is with respect to omega, therefore f of tau is a constant. Cosine function is always even, therefore this function f of tau into cos omega t minus tau is an even function. Therefore we can write this integral minus infinity to infinity as 2 times integral from 0 to infinity. By the property of the integral, we can write this as this is equal to integral from minus infinity to infinity. Here we can write 2 times integral from 0 to infinity 1 by 2 pi f of tau into cos omega t minus tau d omega into d tau plus I into, here note that sine function is always odd function. Integration is with respect to omega means f of tau is a constant function. Therefore this f of tau 1 by 2 pi into f of tau sin omega t minus tau is an odd function. Therefore this integral will become 0. We can write plus I into 0. That is f of t is equal to integral from minus infinity to infinity. Here this 2 and 2 will be cancelled. Integral from 0 to infinity 1 by pi f of tau into cos omega t minus tau d omega d tau. By changing the order of integration, we can write this as f of t is equal to integral from 0 to infinity, integral from minus infinity to infinity. This 1 by pi can be taken outside, f of tau into cos omega t minus tau d tau d omega. Which is equal to integral from 0 to infinity into 1 by pi, integral from minus infinity to infinity, f of tau into here cos omega t minus omega tau, which is of the form cos a minus b. We can write this as cos omega t cos omega tau plus sin omega t into sin omega tau. Therefore, here cos omega t into cos omega tau plus sin omega t into sin omega tau d tau d omega. Now, we split into two terms. This is equal to integral from 0 to infinity 1 by pi into integral from minus infinity to infinity f of tau into cos omega t into cos omega tau, this into d tau d omega, plus integral from 0 to infinity 1 by pi into integral from minus infinity to infinity f of tau into sin omega t into sin omega tau d tau d omega. This is equal to integral from 0 to infinity 1 by pi into integral from minus infinity to infinity f of tau into cos omega tau d tau, this into here cos omega t d omega, plus this term is integral from 0 to infinity 1 by pi into integral from minus infinity to infinity f of tau into sin omega tau d tau, here sin omega t d omega, which is equal to integral from 0 to infinity. Here we write this as a omega. Here the integration is with respect to tau, and this integral will become a function of omega into cos omega t d omega plus integral from 0 to infinity. Here we write this as b omega. Here the integration is with respect to tau, and after the integration we can get this as a function of omega. We write this as b of omega into sin omega t d omega, that is integral from 0 to infinity a omega cos omega t plus b omega sin omega t d omega. We can combine these two integrals as a single integral. We can write f of t as integral from 0 to infinity a omega into cos omega t plus b omega into sin omega t d omega. Therefore, we can restate the Fourier integral theorem as if the given function f of t satisfies the Dirichlet conditions and integral from minus infinity to infinity modulus of f of t dt is less than infinity, then at the points where f of t is continuous, we can express the function f of t as this integral from 0 to infinity a omega cos omega t plus b omega sin omega t d omega, where a omega is given by 1 by pi into this term, my integral from minus infinity to infinity f of tau into cos omega tau d tau, and b omega is given by 1 by pi into integral from minus infinity to infinity f of tau into sin omega tau d tau. If there is some points of discontinuity, we can write this integral, we can write the value of this integral as the average of left limit and right limit at the corresponding points of discontinuity. This is the Fourier integral theorem. Now, let me conclude this session. In this session, we have just discussed the Fourier integral theorem, which is a fundamental theorem in the study of Fourier integral representations. Thank you for listening this class. Have a nice day.